the inclined plane with friction. It's now time to make the problem more realistic, since most surfaces are not frictionless. Assume there is friction between the plane and the box and it is moving down the incline. What is the direction of the kinetic friction force? Since kinetic friction acts to oppose motion, it is directed up the incline in the negative x direction, where the friction force is mu k times the normal force. The friction force acts up the incline if the block is sliding down. And here's a nice key point. The friction force does not need to be resolved into components since it acts along the rotated x-axis. We'll start with Newton's second law again, and we're going to start with the y-axis again, and this time there's a good reason for it. We say that the sum of the forces equals ma sub y equals 0, because it's not moving up and down in that direction. So normal minus mg cosine theta is 0, so normal is mg cosine theta. Now we're going to need that over here. So in the x direction, we have mg sine theta minus kinetic friction is ma sub x. Kinetic friction is mu k times normal, and here's where we substitute the normal value that we found for the y-axis into our x equation. And we have mg sine theta minus mu k mg cosine theta equals ma sub x. We cancel out the m's. We isolate a sub x on the left side, and we move the left side over to the right side, and then we factor out a g. This way we only have to multiply by g once. So to summarize, solve the y-axis first. That finds the normal force, and that is required to determine the friction force that is on the x-axis. The general solution for objects sliding down an incline is a sub x is g parentheses sine theta minus mu k cosine theta. This is a bit different from the result that we obtained for a sub x when there is no friction. We had a sub x equals g sine theta. A common practice in physics is to apply a limiting case to an answer and see if it gives you something that agrees with previous work. Typical examples are letting a variable equal 0 or approach affinity. Which limiting variable would you use here to validate the acceleration for an inclined plane with friction? For the inclined plane without friction, we assume that mu k is equal to 0. We substitute that into our general equation here with friction, and we get the previous result for a frictionless inclined plane. So the equation checks out with previous knowledge. Of course, that doesn't prove it's right, but it is a good indicator that at least we're on the right track. And in this case, we are right. What if we were given an inclined plane at an angle with the horizontal and wanted to know what value of the coefficient of kinetic friction would allow the block to slide down with a constant velocity? Which means what? Means a has to be equal to 0, and it'll be a sub x. Let's use the previously calculated a sub x equation and set it equal to 0, because we have a constant velocity. So I'll put the little a sub x there again. So here we go. A sub x is equal to 0. That's g sine theta minus mu k cosine theta. Divide both sides by g, and then rearrange this. Put mu k cosine theta on the left side, which is what we have here. Divide both sides by cosine theta. So we get sine theta over cosine theta, and the trigonometric identity shows that mu k is equal to tan theta. Let's change the problem just a little bit. Assume the object is stationary on an inclined plane with friction. So you have an inclined plane here, and you have an object here that is not moving. We want to find the angle at which the object will start accelerating down the plane. We will now use static friction. And probably should have drawn it a little more like this. So here is the object. Now, what do you think we should do with this plane if we wanted to make it go down? Well, then we would get this picture here. We'd make this angle a lot bigger. We just showed that for an object sliding with constant velocity down an inclined plane, that mu k has to equal tan theta. We're going to use the same free body diagram this time for the case of static friction. The only difference is that where kinetic friction equals mu k times normal, Fs, static friction, is less than or equal to mu s times the normal. How will this modify our answer? Since we're trying to find the minimum angle at which the box will start moving, that is accelerating, it would be when mu sub s is a maximum, right before the object moves. So the answer is, it's the exact same algebraic formula for mu k, but mu k is replaced by mu sub s. A helpful hint: should you be taking the AP test, when you are asked to draw a free body diagram, they specifically do not want to see forces broken down into components. Therefore, the free body diagram for an object sliding down a rough incline on the AP test should look like normal force here. Right, we'll imagine the incline is like this. Friction force up the incline, and mg straight down. Do not resolve it.